think he fixed it. Okay, great. So it's a pleasure to be here or be virtually here. I hear you've been learning a lot about machine learning and some QCD, and I'm going to give you a sort of overview of my views on the interface between the two. So the talk is about modern machine learning and the Large Hadron Collider. It's a sort of colloquium level talk, but please feel free to interrupt. You know, the Zoom is always very difficult to see if people are following. So if you have questions or things are confusing, please interrupt, but I won't see you if you try to click the little raise hand. So you just have to talk. And I'll definitely hear the talking because I was hearing the feedback. So well, if you have a question, please feel free to interrupt and talk, and I can address whatever it is. In this overview, what's going on here? So roughly, I'm going to sort of give you a very quick introduction to jet physics, which is the realm of the domain in which I'm going to be using some machine learning techniques. And then I'll talk a little bit about the sort of traditional approach to jet physics and collider physics, and then the sort of more modern machine learning based approach. And then I'll go through a sort of list of different applications, a lot of stuff I've worked on, some stuff I haven't worked on, but things that I think are highlights of the development in this field over the last 5 years. So I'll begin with the sort of introduction to the physics of jets. And to get motivated, we should go back to the Higgs discovery. So this is before many of you were probably in physics, but for me, it's almost like yesterday. This is 2012 when they discovered the Higgs boson at the Large Hadron Collider. Before that, people postulated it was a particle, but everyone, I mean, most people, including me, expected not to find it, and you'd find something else like supersymmetry or technicolor. So although it was known and predicted, it was also unexpected. And because of that, they had to be very sure of finding the thing that they claimed they would find. And even though we had a model that was very quantitative and very predictive, it predicted everything about the Higgs boson except for its mass, we still had to be convinced that we found it. So the Higgs was discovered in 3 different channels in the original discovery. The first is the so-called golden channel, which was the Higgs decaying to 4 leptons. This is actually only 0.01% of the Higgs decays this way. So that's 1 in 10,000 Higgses decay to this channel. But it's called the golden channel because it's very clean, because you can measure the momenta of all these leptons and you can add up the momenta and square it, and you get this nice peak. And so what's shown here is this blue is the standard model prediction without the Higgs, and the red is the postulated Higgs. And if you just look at these black dots in the data, you'll see a nice sharp bump. And so even if you don't know anything about the standard model, you would definitely say there's some feature there with the mass around 125. And then you could go down and try to figure out what it is. So it's the golden channel because you don't need much at all to believe there's something there. The next channel, so there's slightly more of these. So Higgs to diphoton, which is around 0.1% or 1 in 1,000 Higgses decay this way. There's also a bump, but you see what's being done here. So the black are the data points. And what they've done is they've fit the data in these sort of sideband areas outside of the bump to this yellow line. And then they've postulated it, they've fit another curve where they parameterize this red curve. And when you draw the yellow curve and the red curve, you can see very clearly there's a bump. But imagine what would happen if you didn't have the yellow curve and the red curve. You just had the black dot. So you'd say, well, maybe there's a bump here, sure, but maybe there's also a bump here. In fact, to help you visualize it, I could remove the yellow and line the red curves. And you see, you know, this is not very convincing by itself. In the context of this, seeing a bump in the same place is convincing, but by itself, this data is unconvincing. And this is more like what we're looking for in beyond the standard model physics. We don't know exactly what we're seeing, and we have to have a convincing signal. And if all we get are these vague little humps on top of things, we're not going to know what's going on. On the third channel that was discovered is the Higgs to 2 leptons and 2 neutrinos. And this has missing energy, so you can't completely reconstruct the Higgs. Instead, you plot something called transverse mass, and you look for a bump in there. But you see the bump for the Higgs, which is the red, has pretty much the same shape as the other standard model backgrounds. They all kind of have bumps. So the only way to find this signal is if you know exactly how much signal there is. So for example, if I remove the backgrounds, you just see something. And there's no way you could find a Higgs boson if you just had this, if you didn't know anything about the background. So the point here is that to discover something, it's nice to have multiple ways to see it, but it's also important to know exactly what you're looking for and exactly what the backgrounds are. And if you have ways of reducing the background even more, then the peak will be sharper. So the name of the game in collider physics is figuring out ways to find signals on top of backgrounds in the cases where there's a small background, where there's a large background whose shape is sort of smooth, and there's a background who you very much need a theoretical calculation to understand. And we'll be kind of talking about these in particular. But you can also ask, so these are the three very small decay modes. At most, we've taken 1% of the Higgses. What else does the Higgs do? In fact, to find out that it's actually a Higgs boson, we need to know not just these decay modes, which are all leptonic essentially, or to photons. We want to know if it decays to quarks. We want to know if it decays to gluons. We want to know all these other things. And we want to identify its couplings and so on. So we can look back at the Higgs boson. So if you can calculate its decay rate, and it turns out 60% of the time it decays to quarks, mostly B quarks, but quarks in general, 20% to Ws, then gluons, tauons, and Z bosons, a very small percent of photons. So why don't we just look for these? Why are we looking for leptons only? Why don't we look for the 60%? Well, how do you see these things? What do quarks look like in a collider? What they look like are collimated beams of particles that we call jets. So 60% of the time, these quarks are jets. Now, what about these gluons is 9%? Well, those are also jets. So far we have 69% jets. And you can ask about the W bosons. We talked about some of the decays of the W bosons. The W decays to leptons, electrons, and muons, but also to jets 20% of the time. So now we're down to 89% jets. Z bosons also decay sometimes to jets, and tauons also are different kinds of jets. So it turns out the Higgs boson almost always is decaying to jets. And these are the things that we use to discover the Higgs, but these are the things we need to understand in order to figure out that it's a Higgs. And again, this isn't just about the Higgs, it's any possible particle we would want to see at the LHC has these kind of branching ratios and decay rates, and so we need to be able to disentangle this stuff. And a lot of the developments in collider physics over the last 10 years are figuring out how to decipher this green stuff rather than these sort of clean channels, which we understand from traditional physics. So what do these jets look like? They kind of look like this. This is a schematic of the Atlas detector, but it's an actual event. So these lengths indicate energy deposits in different regions of the detector. And so there's these two collimated beams, which is what a jet looks like. So microscopically, what's happening is there's a collision here, and these particles like quarks go and they radiate gluons, and then they turn into hadrons. I can give you a kind of better cartoon of it. So we have protons. We look inside the proton you should really think of as this kind of soup of quarks and gluons and things like that. And it's roughly a femtometer wide. So we take two of these things, we bang them together, and sometimes a quark within the proton will bang into another quark at a sort of a size, maybe 100th the size of the proton. Then they start moving out from inside the proton, and here we can use perturbative QCD to calculate what happens until they get to the outside of the proton around the femtometer length scale, where they turn into hadrons that then leave the proton as jets. So this is what we see, and what we're trying to do is map it down to this internal, we're trying to figure out what actually happened from looking at these outside decay products. So here's a jet, and as I said, what we really would like to do is not understand these jets, but to break it apart. So that's not all jets aren't created equal. There's B jets, there's light quark jets, there's gluon jets, there's tau jets. And if we can distinguish all of these different kinds of jets from each other, then maybe we have some hope of actually distinguishing the Higgs, or maybe we can find another particle that say only decays to these or only decays to these, and we can distinguish what's going on. So how can we tell these different types of jets apart? I've spent a lot of time in my research trying to understand different methodology for understanding jets, but what I really want to talk about today is the sort of more modern approach using machine learning. So right now, let me pivot to talking a little bit about machine learning, and then I'll come back to this question of jet discrimination and show how machine learning helps. So what I want to talk about is modern machine learning, and this is in contrast to sort of traditional machine learning that has been done in collider physics for 30 years or more. So modern machine learning, the way I think about it is as follows. So the traditional approach is you think really hard about some process. For example, we want to know what's the difference between a quark jet and a gluon jet. We think, this is what I know about quarks, what I know about gluons, and I come up with some observable that I think will tell them apart. And I've actually done this. So this is not just a cartoon. This is really how people think about things, or at least did think about things. So you have some guess, and then you run some simulations like Pythia or Herwig. And then you take the output of these simulations from your observables and you combine the best ones. And this is a kind of a traditional machine learning approach where you take these high-level observables, things like the number of particles in the jet, or the mass of the jet, or the width of the jet, or the end subjettiness, or things like that. And you combine them together with a rather simple neural network or another approach. And these are basically equivalent for this process. And then you see if it works, and you apply it to data, and then you validate the physics from the physical insight on the data. And the modern approach is different. You come up with some innovative algorithm that you kind of pull off GitHub or you read in some blog post, and you try it out, and you run some simulations, and then you apply the data, and then you validate the algorithm. So they're really different approaches. The modern machine learning approach kind of sidesteps the physics altogether. And eventually we're hoping to come back from this, algorithmic searches and algorithmic discovery to physical insight. But right now we're sort of saying this actually, for things like distinguishing different types of jets, it doesn't even matter if we understand what's going on. We just want to see that it works. And that's kind of where we are. And I'm going to talk a bit about how this works, and then maybe also a bit about how we might get back to the physics, which is really a goal that hasn't been realized yet in machine learning. So how does it work? What's the game about? So the way I like to think of it is a sort of a game of hammers and nails. So we have a bunch of hammers, which are these computer science techniques for machine learning, things like convnets and recurrent networks and variational autoencoders and reinforcement learning and point cloud networks. And basically you look at what's coming out of Google and Facebook and OpenAI, and you see what they're up to, and you read the CS papers, and there's a lot of really fast advancement going on in computer science. And then you say, well, I'm a physicist, so these are the hammers, and I have a bunch of nails, a bunch of problems I want solved, like top tagging or W tagging, quark gluon discrimination. I'll talk about some of these things today, tagging light quark jets, more experimental things like jet energy scale calibration, heavy ion physics. And so you want to see which of these nails can apply to which of these hammers. And that's basically what's been going on in machine learning in the last 5 years. People find some CS paper and find some nail, and then they match one of these to one of these and write a paper. And I'll talk about how that works. Before I get going, I want to distinguish a little bit what we do in physics from, and this is maybe for more of the computer science background audience, that physics, really the domain of physics is distributions, right? So there's something that's very different in distinguishing signals from background in a physics process from telling apart cats and dogs. And the difference is that if you have some process like this jets in this picture, it's not a cat or a dog. What it is there's a probability that this set of particles, this set of pions and kaons that we see in the detector, comes from a quark hypothesis, and there's some probability that it comes from a gluon hypothesis. There's no correct answer. The actual data is a linear combination of the two, and there's even interference between the two, although the interference is often very small. There's this basically a 1,000-dimensional phase space, or if you include the actual experiments, it's as high as maybe 10 billion or 100 billion dimensional. And somewhere in this space, there's this overlapping region of this signal hypothesis and this background hypothesis that we want to distinguish. So really what we're trying to do is map out these probability distributions. We're not trying to find actually the individual truth identity of the actual event. I mean, this is important for knowing what the actual best we could possibly do is. There's not a right answer always, but that doesn't mean that we can't do very well. So the goal is to really measure these differential probabilities, not to distinguish an individual event, right? So we want classes of events, and we want, if you have an individual event, you can say absolutely nothing about whether it's the Higgs boson or not. If you have 100 million events, then you can start saying something. But if you have 100 events, you can start saying something. But each individual event, there's no correct answer, and there's no way to figure out what that actually is. It's just not well defined physically. Okay, so now let me come back to one of the examples I was talking about, quarks versus gluons. So let me just start with a little bit of the theory from the traditional approach. So the traditional approach would be, let me think about quarks and think about gluons. So a quark is this, there's 3 colors of quarks. So there's a chance of radiating it, and the color charge is basically 3. So this is like electric charge, but for color. And a gluon is basically color charge 8. And so just like something with more electric charge would radiate more photons, something with more color charge would radiate more gluons. The effect is that you have roughly twice as much chance of emitting a gluon. And we're using this not quantum mechanical, but this sort of semi-classical picture of radiation, where particle moves along and there's some probability of emitting a particle. And it's not that different from an accelerated particle emitting photons. This semi-classical picture is actually a very good leading approximation to the actual quantum mechanics. So the bottom line is that gluons are roughly twice as likely to radiate than quarks. And the effect of this is that these jets from gluons have roughly twice as many particles, or more particles at least on average. They're bigger, they're fatter, they have more of everything. So this is the physical insight. And then you take that and try to construct observables that are sensitive to this that might be able to distinguish quarks and gluons. So for example, I can count the number of particles. So I say, well, since they're radiating more, I should end up with more pions. So let me count the number of pions I get. And you say, yes, in fact, at least in simulation, gluons have a distribution of the number of particles, which is larger than the distribution of quark. So I could use number of particles as a way to tell apart quark jets from gluon jets. I can't tell for an individual jet, there's 100% overlap of these samples. So if I told you I had one event, I can't tell you if it is exactly a quark or a gluon. There's no correct answer. But if I have an ensemble of events, I can tell you what the probability is that it's a quark or gluon. And if I have enough of these, I can tell you very, very well what the probability is. So what do? So you take all these ideas that you can have that are sensitive to the differences between quarks and gluons, number of particles, number of subjets, the shape of the jet, the width of the jet, the mass of the jet, and you take them all and you calculate them, and you calculate them in simulation, and then you throw them into some traditional machine learning method or just a traditional multivariate method, like a boosted decision tree, and then you combine them. And so this plot just shows I'm going to show a few of these, so I should explain it. This is like a ROC curve, a receiver operator characteristic, but I've taken, instead of plotting the signal efficiency versus the background efficiency, I plot the signal efficiency divided by the square root of the background efficiency. So this is roughly a proxy for significance. So the higher this curve, the more significance improvement you would get by using that combined observable for discrimination. So this shows you that, for example, using the number of particles, you could get around 1.5, say, which is a 50% improvement over some baseline. If you use the width, you would get a little better, almost a factor of 2. But if you combine all these things with a boosted decision tree, you can go around 2.2. So these are kind of the benchmarks that we can look at. This is about as good as you can do by thinking. And what we want to see is how well you can do using machine learning. So this is stuff I did, but it was also one of the earliest approaches to machine learning in collider physics. So I'm going to talk about it a little bit more detailed than some of the other stuff that I might go through fast. So our idea here was to use convnets, this was about 4 years ago, or yeah, something like that, 3.5 years ago, when they were starting to get used for image processing. This is when they finally solved the handwriting recognition problem, and there was lots of rapid advances in computer science. And the idea of a convolutional neural network is that you have a bunch of layers of a network that get smaller and smaller and are sensitive to different sizes, and they're sort of translationally invariant. So it's used for image recognition. And I guess I don't have time to really go through the details of these network architectures. Presumably you've had talks about them already. So I'll just summarize. The idea is that there's a technique used for image recognition, and we wanted to use it for collider physics. So to do that, you need to turn the collider physics data into an image. So the way we did that, and this wasn't our idea, people were used it for traditional approaches, but it fits very well in this convnet structure, is you take the energy deposits in the detector. So we just say, take this square and take the amount of energy and interpret it as a color. So the more energy you have, the higher the intensity of that pixel. And what we did is we just used 3 different colors. So we said red is the energy of charged particles, green is the energy of neutral particles, and blue is the number of charged particles. These are 3 things that you can actually measure in the data. Red, green, and blue are just artificial names for these things. They're really just 3 inputs to a convnet. Then we kind of pre-process it and input it to a neural network. I'm skipping all the details of how it works. But the bottom line is that the neural network works really well. So I'm comparing here the boosted decision tree from 2 slides ago, which is this blue output, which was around 2.2 or 2.4 in our recasting of that, 3.3. Now, when we did this result, I should say I was overwhelmed because we spent a lot of time thinking about these variables and basically thought of everything we can think of that's physically motivated and put them all together. And it really saturated around here. And somehow coming out of the box and shoehorning this stupid image recognition technology into this problem that's totally ill-suited for, you do significantly better than everything we did with all this physics insight. And it's a lot easier. You don't even have to think about it. You just run it. And this was, to me, the thing that convinced me that machine learning is really the future of collider physics. There's no room anymore for spending years thinking about the physically motivated variables when you can do a lot better by running the machine learning, and then we just have to figure out what's going on here and why it works. But the fact that it works is really extremely convincing and very impressive. Let me talk about another example that has gotten a lot of attention, which is top tagging. And again, this is another problem that had a traditional approach in collider physics, but then was reinvented in machine learning and done better. So let me explain what's going on. So what is a top quark? A top is the heaviest known quark. And because it's heavy, it has a large coupling to the Higgs boson and a large coupling maybe to new physics. It's also the least well-studied quark. So we're hoping that it'll give a signal of beyond the standard model physics. So you might have something like this thing is supposed to be a KK gluon, which is some particle in Randall-Sundrum model, but it could be anything. Some resonance that decays to a top anti-top pair. And then these are just standard model particles, so they decay in the usual way to a bottom quark and a W boson. And then the W decays to an up and a down quark. And then as I explained before, each of these quarks show up as a jet. So this di-top event, or this heavy resonance decay, shows up in the detector as 6 jets. So here's an example of a CMS measurement that shows a 6-jet event. This is a candidate top event. And we've seen millions of these now at the LHC, but before it was started running, and at Fermilab and previous machines, they saw a handful of these. Now, what's interesting is that the LHC, if this thing is very heavy, so if this thing is light, say, the top quark is roughly 175 MeV, so 2 top quarks is roughly 350. So this thing is a little bit above 350, say 400. These tops will be produced pretty much at rest, and these jets will go far apart. On the other hand, if this thing is extremely heavy, like a TeV, then these tops will get a lot of energy and be moving out like bullets away from the decay point. So you might end up with something like a 500 GeV top, and then when it decays, all of these decay products will all go off in the same direction. And so what you get is, instead of 6 jets, you get this kind of collection of all the decay products of one top go one way, and all the decay products of the other top, or the anti-top, go in the other direction. So now it looks like 2 jets. And the problem with 2 jets is that there's a much, much bigger background for 2 jets than there are for 6 jets. So 6 jets is pretty rare. You need to produce 6 separate production of jets in the standard model. But 2 jets is extremely common. It's the most common thing at the LHC. The cross-section is like a nanobarn or something ridiculous. And so there's an enormous number of them. So this is an example of, you might have some heavy gluino decaying to tops, and the standard model dijet background is orders of magnitude larger. So this might be 2 or 3 orders of magnitude larger. These are stacked plots, so you just can't see any bump at all on top of this background. So what do? How do you find this kind of signal on top of this background? Well, that leads to, so here's an example of a TT bar event in this boosted regime. So we even see these in the standard model. This isn't a KK gluon, but we have examples of these because the LHC has seen so many tops. It's seen quite a number like this. So how do we find these? And the key is saying, well, yes, it looks like one jet, but if you look inside it, it's actually a new type of jet. So all of the particles go the same, but actually you can tell that a top jet actually has these 3 components within the jet. So there's the up, the down, and the bottom would be separately identifiable subparts of the original top jet. So this was a new concept that came about in particle physics maybe 10 years ago, and really revolutionized the way we think about jet physics at the colliders. And now there's a whole dedicated conference boost, which is going on this week actually, dedicated to studying these kind of things. So the traditional approach to understanding tops in this context was, well, first you look for something like a fat jet. So you look for a big jet, so like a R equals 1.2 jet was what the original top tagging studies did. And then you look for subjets within the jet. So you cluster the jet, and then you analyze the subjets, looking for things like a W, and you look for the top mass peak, you measure the helicity angle, you can do, and you cut these large backgrounds down to something relatively small. So this is how top tagging was traditionally done, and it works really quite well. But along comes machine learning. So this was the study I just said, which was one of the first top tagging studies that showed that boosted tops can come on this ROC curve, which is signal efficiency versus background efficiency, is around here. So what this means is, for 40% signal efficiency, so you keep 40% of your tops, you reject a factor of 80 of your background. So you keep almost, roughly half of your tops, but you throw out only 1 in 80 of your tops get through, of your background jets get through. So this was actually extremely impressive at the time, and what they used to measure things like these top jets in data. So this was something that they found with CMS using this what's called the Hopkins top tagging algorithm. But now you see machine learning. So there was a study recently last year comparing, I don't know, a dozen or more different machine learning algorithms to find tops, and you see they do significantly better. So at 40% significance, they're doing an order of magnitude or 2 orders of magnitude better at top tagging. Here's a table from that study, trying to be quantitative. There's a lot of numbers here. You can see which number that you like best. So for example, at 30% signal efficiency, the number of background events that they reject, the background fraction, is this 1/epsilon b. So that's the vertical axis here. So we're basically looking at, those numbers in that column are the points along this line. I'm sorry, at this line at 30%. So those numbers are here. So 9, 14, 11, 22. So the bottom line is that the best algorithm, which was this particle net with 1298. So we're keeping 30% of the signal, but we're rejecting only 1 out of 1,300 of the background events are getting through, right? To give you some sense of that, so these used 800K training and 200K test samples. So keeping 1368 out of each, for each 1368 backgrounds have to get through for one to look like a top. That means that out of this 200,000 event training sample, only 146 background events survive. So even though these are very large samples, we're still kind of sample limited because of the actual amazing efficiency of these algorithms. And again, compared to say the Hopkins top tagger, it would be around, I don't know, 2,000 background events survive. So we're doing an order of magnitude better in rejection. These are extremely impressive numbers. And again, from someone who has worked on the traditional approach, this is really mind-boggling. They did things that we didn't think possible. They're finding structure. They're finding, gold in the dirt. It's blood in the stone. I didn't think there was anything there. And these studies, some of which I was involved in, really did show that there is stuff in that background. So I'll talk a little bit about some of these approaches. And again, a lot of this is just hammers and nails. They're taking this particle net, for example. So the particle net, which did the best, this was this paper by Guskus and Chu from last year. So what the idea is, it's a point cloud approach. So this is something they use in self-driving cars, where you send out some LiDAR or something from the car to measure the surroundings, and you get a point from each place it hits, which is a distance, but you don't have a full 3D image of the surroundings, so you just have a set of points. And here, this is like a point cloud version of a plane, where there's no depth to this. I mean, there's depth to each individual points, but you can't see through it. So it's not actually a 3D image. So point clouds are a nice way to represent this because they're intrinsically unordered points, just like particles are intrinsically unordered. And this turned out this technique was very powerful. But basically what these guys did is they took some algorithm from Facebook or Google, I can't remember which, and they just applied it to particles instead of point clouds, and it worked really well. So they took the 2D coordinates in the rapidity azimuthal angle space as input, as the directions, and then they ran these, they tried to represent the data with the point cloud architecture, and they added some additional features, and it worked really well. And uses this sort of edge conv structure with angular distance measure. And there's lots of details you can understand. I should say there's a whole set of papers also involving this intrinsically unordered representation of the data. So a lot of what's going on in ML is people take architectures and try to figure out which architecture is best suited to the problem, and try to kind of, again, shoehorn the technology developed for a different purpose into particle physics. And it tends to work. This was actually tried out in data, not that particular point cloud one, but a lot of these modern machine learning methods. So this is the CMS simulation, which uses this deep AKA tagger. This is basically just a deep network that uses the particles as input. So it uses the kinematics, like the 4 vectors of the particles, and they plug it into a deep network, some kind of recurrent structure. And you see it does very well. So this is actually tried out in simulation, but using a full simulation with a detector and everything. And it seems to work better. So this deep network seems to work better than some of these image-based approaches. And there's a bunch of other different algorithms that they tried. And it does seem to work better if you put more information like track info and heavy flavor tags. Atlas also did it. So what Atlas tried is using not just the 4 vectors, but actually the topo clusters, which is this low-level information that Atlas has. So before you regress out that there was a particle there, you just grew the raw energy deposits into the calorimeter. And they have this topo cluster structure for combining different types of calorimeter input. And they put those topo clusters directly into the deep network. And it actually does, so this is the topo, and the BDT is the sort of high-level inputs like the Hopkins top tagger. So again, we're seeing directly in simulation, but they've also tried this out in data, that it tends to work better. I mean, it's hard to validate it in data, but you can certainly try it in data. So again, they're seeing that using the full experimental information, it's working better with machine learning than it did with the traditional approach. The next application I want to talk about is pileup removal. So this is, again, another nail that has been a bugaboo of the LHC for a while. It's the LHC has, so what is pileup? the way the collider works is the protons are in bunches. So there's around 10 to the 11, 100 billion protons in each bunch, and they move around. One bunch goes this way. Well, there's around 2,000 bunches in the ring at any time, and some of them go this way and some of them go that way. And then they narrow them down at the beam crossing to a micron or so, and they collide them together. So it's not just like a continuous stream of particles. The particles are in bunches, and that actually helps with a lot of the experimental analysis. I mean, it would be impossible to collimate everything down. So this is the way the experiment has to work. When you have a collision, suppose you're interested in something like a top TT bar event, right? So out of these 100 billion collisions, you would have, they're colliding a billion times a second as well, because they're moving at the speed of light. But most of these collisions aren't very interesting. The bunches, all the protons kind of glance off each other and you don't get something interesting. But every once in a while, one in every million collisions or so, you might get something like a top, or you might get a hard dijet event, or something that passes some of the trigger thresholds that looks like this. But the problem is you have 10 to the 11 protons in a bunch. So when you get this, you also get a lot of other protons banging together too. So this might be the thing we're interested in, but you get all these other secondary collisions, and they're not exactly at the same point in the beam, but they're nearby, and you might have 10 of them, might have 40. We're getting to the point for the high luminosity LHC where we get out 200 collisions per bunch crossing, and might get as high as 1,000 for the high luminosity LHC. So what this means is, if you say you're trying to do something like look at the mass of the jet, or the dijet mass, right? If you're looking for a resonance, you want to look for a peak in the dijet mass. So if you look at the dijet mass from the actual thing, we're cheating here using the fact that we know what it is. It might be a resonance at 500 GeV, which is here. But once you include pileup, it moves all the way up and it gets much, much larger. So the problem is the pileup is just the soft radiation that makes everything heavier and more energetic. So if you actually saw the data that looked broadly distributed, well, really what you're looking for is this sharp peak. So the goal for pileup removal is to reverse this and say, can we figure out what came from this primary interaction, what came from these secondary interactions? And we have some tools to do it, right? We have in particular the tracking system. So this is an actual event display from Atlas. And what you see here is you can localize the particles from their tracks. And you can see that some of the particles go to this primary interaction vertex, but most of them don't. So this is very good, but you can only see charged particles, because only charged particle leaves tracks. And only about 2/3 of the particles of the LHC are charged. So this is helpful, but it's not completely solving the problem. And we want to know is, can we learn something, say, about the neutral particles from the charged particles, and can we use all this information and combine it to remove the pileup radiation? So the method, there's a few methods doing this, but I want to talk about the one that I worked on, which is called Pummel. So the idea is we use this confident architecture where we have the 3 inputs that we can measure. We can measure the energy deposits from the leading vertex. We can measure the pileup from the charged particles, the energy from the pileup particles, and then we can measure the neutral particles. I use bigger boxes here because the resolution on the neutral particle energy isn't quite as good as the pileup energy. So again, we have like a 3-colored neural network, and we can put that into a convnet. And then what we try to do is not distinguish signal from background, but we're trying to regress out the leading vertex neutral particles from simulations that we can train it on, given only these experimentally measurable data, right? So this hadn't been tried before. It's a very, very difficult regression problem, a highly multidimensional regression problem. We're trying to find out what the true distribution is of the neutral particles in the event from not having measured them and using correlations and information about how particles are nearby. So we put this into a convnet and used it for regression, which is basically you run it backwards to see what you get. And then you see where it lights up on the channel that's associated with the input that you didn't have. And it works really, really well. So here's an example where this is the truth. These are just sample events. So here's a truth event where you have, this is the neutral radiation from the leading vertex that we don't have. Here's what you get when you add 140 pileup events. And here's the regression you get out of Pummel. And you can compare it to some other methods in the market. These are traditional approaches, puppy and soft killer. And you can see they don't quite do as well. You can see there's some particles they think they're there that aren't there, while Pummel agrees really well. And you can quantify this as well. So you can see, for example, if you look at the jet mass, so this is this plot I showed you before. If you look at the mass, you start off with this broad distribution that's much larger, and you're trying to regress out the x-axis here. So what you see is this, and you're trying to regress it down to this truth information here. And Pummel does really well. So the truth is the green, and what Pummel gets is the black. So you get almost exactly the right truth level information, even though the actual data looks like this using Pummel. It's also remarkably insensitive to the number of pileup events. So so here what we're showing is Pummel with trained on 140 pileup events, and you see it's really, you get the same regression. The jet mass correlation coefficient is really flat as a function of number of pileup events, which is exactly what you want. This actually works on data. So this was an Atlas study using similar approaches with a content image regression that actually as a function of number of pileup events, they use it for missing energy. So this is the difference between the missing energy and the truth values missing energy using the same content architecture is extremely robust. It's very insensitive to the number of pileup events. And this is exactly the kind of thing we're going to need going to the high luminosity runs of the LHC. A similar, a different machine learning approach called PummyML, which was developed by some CMS folks, uses the same GraphNet, a kind of GraphNet order-free architecture. So it's not convnets, but involves graphs with points and links between the points, and then feeds the result into a dense network. And so this PummyML is also pretty insensitive to the number of pileup events. It's not quite as flat as Pummel, but also works pretty well compared to some other traditional approaches. Next, let me talk a little about unsupervised learning. So this is an exciting area of development in machine learning in particle physics. Instead of something like supervised learning where you train on signal and background and you try to discriminate them, the idea is unsupervised learning is you just try to learn what the actual distribution looks like, and then you can do things with it. So an example of this that I've worked on is you're trying to learn the actual probability distributions of a sample, right? So now we have these simulations like Pythia and Herwig, which populate a highly multidimensional space, but it's very difficult to tell from those what the actual differential probability is in that region. But it's something that can be learned. So what we tried doing is modeling, so we took you take an event, you take a jet, for example, and cluster it. So there's an iterative clustering algorithm which turns the jet into a binary tree. And then at each node of the binary tree, you can evaluate the relative probability comparing over an ensemble of trees for a certain branching as a function of distance along the tree. So these numbers are the log base 10 of the probability. So this is 10 to the minus 3 and so on for this particular structure. And the color represents how hard the particle is in the jet. And so the idea here is that we're just learning the distribution of jets. And so then you can say for a given jet, you can compare to the differential probabilities. You can learn, say, a sample of quark jets, learn the probability distribution, have a sample of gluon jets, learn the distribution of, learn the probability distributions. And then if a given jet, you can see what is the relative probability that it's a quark or a gluon from just evaluating on these two separately changed unsupervised architectures how it works. And again, this is very much aligned with what I was started with, which is that we're trying to learn just differential probabilities. That's the domain in which particle physics applies. And so one thing you can do with this is visualize the discrimination power. So part of the goal of this is interpreting the output of the machine learning. So for example, we talked about top tagging. So is this a boosted top or a QCG jet? Again, a particular point in phase space has some probability of coming from your top hypothesis and some probability of coming from the QCD hypothesis. So what we're able to do is take that same event and ask, what is the probability that it came, that coming from the quark hypothesis, because we have a network trained just on quarks or QCD events, and what is the probability that it came from top jets when we have a different probability? And then we can compare the relative probability for those jets. And then we can look where along that tree is helping tell apart whether it's a quark, a top, or a QCD jet. So what this is saying is that these two nodes are the dominant information about whether it's quark or gluon. And so what that says is that top jets have this typical structure where you might have some soft radiation early on, and then you have this hard branching, and then you have another hard branching. And of course, what that represents is the top decaying to a W, a B, and then decaying to a W, and then the W decaying. So again, we're not putting in anything about particle physics here. We're just training it on data consisting of pions, but it's able to distinguish this actual structure and tell you what's going on. So what can you do with it? Well, you can do discrimination if you want. Again, we're doing an application to discrimination, but it's an unsupervised training. So we're just training it on jets from quarks and training it on gluon jets. And it's able to say for a given jet that it's consistent with the quark hypothesis or the gluon hypothesis. And then you can look at what you could break it down and see what aspect of the tree was useful for doing that discrimination. You can also distinguish two simulations. You can see why is Pythia different from Hurwig and tell apart the two simulations from the data. A related idea is a paper by Andreasen and Nachman called Doctor, which is a way to use, so it's a sort of another unsupervised approach where you try to use the relative weights for tuning. So the idea here is you want to you have some data and you want to know which Monte Carlo parameters, what value of alpha S, what value of the parton shower length, what value of the hadronization parameters, various things in your Monte Carlo that you want to tool. And right now they're tuned by sort of just fiddling them one by hand. But what they tried doing is putting those Monte Carlo parameters directly into the simulation and trying to regress out those Monte Carlo parameters. And so what they're able to say then is that you can, once you have the data as a function of the parameters, then you can re-rate one set of data to a different value and then find the minimum. Right? So they learn it. So here's an example where they learn the data as a function of alpha S, and then they can find out which value of alpha S is the best, and then re-weight the events to the correct event, correct value once you have it. So this could be not only a very efficient way to tune simulations, but you could also re-weight the simulations to the data if you know what the best fits are directly on the data. So following up on that idea was another paper by Andreasen and Nachman, but also some other people, called Omnifold, where it uses machine learning to unravel the mapping between detector simulation. So there's event generation, which is like Pythia, detector simulation, which is like Jaeon, and the actual data. So the idea is to learn these mappings so that you can unfold the data directly into the simulation, right? So what's going on now is that if you have some data that you want to compare to a theory calculation, the experiment has to devote, a set of graduate students and postdocs to actually working out that observable and figuring out all the uncertainties and unfolding the actual detectors so that you can compare to the theory directly. And this is a machine learning way to do that. And so they didn't have actual data and detector, but they had some toy of it, which was using Pythia and Hurwig and pretending that Hurwig was the data and Pythia was the simulation. And they were able to actually unweight this distribution, which is the software jet mass. They have, half a dozen of these that they tried. And it works really well. They're able to regress out the truth information in a sort of model independent way directly from knowing these mappings. They're not doing it observable by observable. They're doing it data once and for all the data. So this unfolding is related to another experimentally motivated idea, which is weak supervision, right? So again, I can write these three categories. We talked a lot about supervised learning, where you have, say, pure samples of quark and gluons, and you know what they are, and they have labels, and you try to learn those labels in their testing data. Unsupervised learning, we also talked about, where you have no labels at all, and you just try to find patterns. So we just learn the quark distribution, learn the gluon distribution, and then afterwards we can compare them or not. Weak learning is somewhere in the middle, right? So you have some sample, which is a mixed ensemble of quarks and gluons. And this is actually what the data has, right? So you don't have pure quarks and gluons. You have, maybe you have 80% quarks and 20% gluons or something like that. And you want to be able to train directly on those mixed samples rather than having pure samples. And so what we were able to show is that, this was by Derry et al. What they were able to show is that using these kind of high-level inputs, that they can do as well with mixed samples as they could with pure samples. So that's kind of the coincidence of these two lines demonstrates that. It'll take a little while to figure out what's in the plot, but that's what it means. So they're basically showing comparing blue and green is fully supervised and weakly supervised. You can try with more complicated observables. So what we tried is quark-gluon discrimination with jet images, but using weak supervision. So instead of pure samples of quarks gluons, we just gave it mixed samples, because this is actually what you have in the data. And what this really means is that you can train it directly on data. What's so important about this? So first, let me explain this plot. Again, this is some metric of discrimination power. The fully supervised is the red. The weakly supervised are these other various curves. So for example, depending on how pure a sample you have, if you have a 20% pure sample of quarks, you can do almost as well as a fully supervised. I should say even with 30% or 40%, you're not doing bad, right? This is all, this whole axis only goes from 0.79 to 0.87. So you're doing nearly as well as the fully supervised case with weak supervision. Right? So why is this interesting? It's interesting because it means you can learn complex discrimination directly from the data. You can train your quark and gluon discrimination. All you need is 2 samples that have different quark and gluon content. And we have plenty of those. So the dijet sample has a different quark and gluon content from the W plus jet sample. And we have hundreds of billions of events in both. So you can just train, you're basically training the machine to learn the differences between those 2 samples. And the differences in the 2 samples are presumably differences between quark and gluon. They may not be quark and gluon, you don't know, but you need some theory to tell you what that is, but it can still use them. And then you can test it on a 3rd sample and see if you can regress out the quark gluon fraction and then test your hypothesis that it is quark and gluon. Or maybe you'll find some other difference and learn some physics associated with it. But the real point is that you can do this training directly on data. You don't need to use simulation at all. The main advantage of simulation is that you have pure samples with truth labels, but weak supervision shows that you don't need truth labels to be successful at discrimination tasks. Okay, the last thing I wanted to talk about is decorrelation. So this is also an exciting area that has received a lot of attention in the last 2 years or so. So this is a way to introduce adversarial networks. Again, here's our Higgs plot. Suppose we want to find this bump, right? You can train a network on the signal and the Higgs in the background, which are diphotons. But if you do that, and then you plot the actual data, it might be very good at distinguishing signal and background, but you wouldn't be able to trust your bump, because if you're training it on something that has a bump, and you plot it as a function of mass, and mass went into discrimination, you're basically just going to sculpt your background to look like a bump. So even if there weren't any signal at all, because it was supposed to remove that region that had the bump, it would sculpt a bump into your data. So that's very dangerous. So one thing you can do is this adversarial approach, which was kind of it's something that they use in learning games, for example. They used it to learn chess and Go, where you have 2 networks paired off each other. So you would have one network trying to find a good discriminant between, say, Higgs and diphoton, and another network tries to guess the mass from the sample. So you train the adversarial network, the adversary tries to guess the mass. And so the best training, so if you train it well, then it's completely flat as a function of mass and totally decorrelated with mass. And once you have this, then you can plot the mass, and you can trust that if there's a bump there, it's only because there's a signal, because you've removed all of that sculpting. And what they showed in this paper by Luke, Kagan, and Kramer is that the significance is significantly improved for, say, a Z prime mass search once you've done this adversarial training for a mass pump. Turns out you don't actually need this adversarial. Adversarial approaches are very difficult to train because you're essentially looking for a saddle point instead of a minimum. So there was a paper which I forgot to cite by Kashika and Shi that showed that you can actually do an alternative approach called DISCO, discriminant correlation, which uses just a loss function instead of an adversarial approach, which has a saddle point. It just tries to find a global minimum. And what we showed in this paper, which should be out next week, is that you can use the same decorrelation method to machine learn directly a background-driven discrimination. So what we tried to understand is this ABCD method. This is one of the most standard methodologies to use for experimental background estimation. The idea here is that you have some background, which is roughly independent of the signal. The signal peaks in some region, say A. So you have two discriminants, F and G, which you plot here. And you have a signal region A, and the background is roughly independent. So then you can estimate the background of signal A by measuring it in regions C, D, and B, and then saying the number in A is just NB and C divided by ND. And that holds if the two observables are independent on background. And traditionally what's done is you would say, let me take one observable as like mass, and the other observable is something totally uncorrelated with mass, like rapidity or a number of particles or something like that. Well, that might be correlated. But you try to pick something that's totally not connected to mass that you assume to be uncorrelated. And this is how they do the experimental analysis. And then you would use this to decide this, right? So the point is there's no signal here. So you can just measure these three, take BC divided by D and predict A without ever using any kind of simulation. But of course, you do need to know, you need to estimate the uncertainties, and to do that, you need simulation. So it's not entirely theory independent. What we want to see is if you could learn this other variable given a fixed first variable, or you can learn both of them. So we have these two methods, single disco and double disco, which we use to test the ABCD method. And it turns out it really works really well. So you can learn both methods using this disco loss function. For example, we use our parity violating Schwartz search. This was a study by Atlas that used the ABCD method. The Atlas features are over here. So this is background ejection is the vertical axis. This is signal contamination. So if you have signal contamination, then your p-value, your actual significance for discovery, will be lower. So you really want lower signal significance. So using these disco methods, you get slightly better background reduction, but significantly lower signal contamination. And what that turns into is significantly improved discovery reach in these kind of background-driven searches. Good. So let me conclude. I talked a little bit about various kind of trying to introduce modern machine learning and what's going on in collider physics. The field is growing so fast it's nearly impossible to keep up with the developments. The number of papers is exponentially growing, and it doesn't look time to stopping. More and more people are getting into it. There's been a lot of really impressive progress on the standard nails in collider physics, quark tagging, top tagging, quark gluon tagging, anomaly detection. And there's a lot of work recently in trying to go towards interpretable networks and so on. There's new observables, there's new data representations, improving experimental analysis. There's a lot of different areas to work on it. I think the way I see the future of this, so the past has sort of been this hammers and nails approach, just take some CS technique and apply it to problems in particle physics. I think the future is really going to be learning physics directly from these methods. And I'm really excited to see how we can close the loop and go back to understanding the physics rather than just using discrimination. I wanted to call attention to this, this review. So if you want more information, there's this nice thing that Ben Nachman set up, but is sort of constantly updated. Let me see if I can get there.
Okay.
Losing you there. Yeah, so there's this, hopefully you can see it now. So there's this website, Living Review, which really just, I mean, there's some reviews which you can learn from, but there's also, you know, really a list of pretty much every paper in machine learning and particle physics. So it's a great way, if you're interested in a certain area, you can just get at the work that's relevant. So I think this is great because it keeps getting updated. The field is growing so fast that these reviews are pretty useless because they're out of date pretty much before they're written. So this is a better way to get access to the information. Let me put that link in the chat. You can play with it. Okay, so that's about it. Thanks for your time. Questions?
Yes.
Can I start asking a very quick question? Yeah, in your slide about ABC disco thing,
Yes.
is there any magic in having two features, or can we have more features?
Well, the ABCD method works with two features because of this formula. So these N, B, and C, and D are just the regions. We're just drawing rectangular cuts and counting the number of events in these regions. So we want observables, and then the experiment will just optimize where to do the cut and then count these. It's just a cut and count measurement of data-driven background estimation. All they have to do is use these observables coming out of the neural network. Now, in principle, you could have non-rectangular regions, and you can do much more sophisticated things. But the more you do that, the much harder it is to calibrate these things on data. And a lot of what drives the interest in ABCD is its relative simplicity. That you just count some events, and a lot of experimental systematics drop out of the simple ratio. If you try to draw funny shaped regions, then the systematics get very complicated. Doesn't mean it can't be done, but I think for the purpose of improving this very old method, we just kind of wanted to do what they do directly in these experimental studies. I mean, there's thousands and thousands of experimental papers using ABCD.
So maybe we can extend this ND/NC over ND formula to the case where we have like 3 features or 4 features, right?
You mean like in 3 dimensions and 4 dimensions?
Right. Yeah.
Yeah, you could, and maybe it would help. That's an interesting idea. To still use rectangular cuts, but have multi-dimensional cuts.
Right. Yeah. Thank you.
Can I make a question?
Please.
You say at very early pages of your slide where quark vs gluon. My question is about the pages about some 3 layers colored RGB, that one of layer represent the energy of charged particle and energy of neutral anyway something. Yes. This question, no, never mind. If you say there is a meaning of layer, physical meaning of layer, but I don't. But if the layer is
layer here is a technical word for the structure of the convnet. So it's just the layer. So each time you have a layer, then you have a convolutional structure on that layer itself, and then you combine the different layers together to get the final output.
My question is,
I don't know the slide with the actual network architecture, but the layer just refers to the convolutional step. I mean, you have these different kinds of, you have a dropout layer and other kinds of elements within the network. I'm saying don't get tied up with the word layer. I'm not sure I understand your question, but I think it's a semantic one.
Is a layer is purposefully constructed for a physical meaning or vice versa? Make a layer and
yeah, I mean there is physical meaning, right? The energy of the charged particles, yes, the energy of the neutral particles, and the number of charged particles all have physical meaning, right? They're observable things that you can interpret. But when you start combining them together, I mean, we're combining a number with some energies, they're not really in the same category. So once you put them into the network, you lose all control over the physics interpretability. We were just saying that there's, really what you're getting at with these convnets is spatial correlations, right? So the idea is that the amount of energy that comes here is coordinated with the energy that comes there. So if you have a gluon, you might have kind of regions, you might have like, these convnets were used for image recognition. So you would have a face and you'd have 2 eyes and a nose, right? And it looks for structure like a nose. And a nose might be a subjet. And it might be that, there's the subjects for gluons have charged particles that have these nose features, and neutral particles don't, and number of particles. And you have basically 3 different ways to find different kinds of structures. And then the network somehow magically finds all these things and figures out what's relevant. So we're just kind of giving you lots of opportunities to find these things. We did look back at it and see which layer is most important. And the red and the green are the most important, but the red has the best resolution, so that's kind of why.
I got it. I was thinking about it was some hidden layer in machine learning, but
Yeah, there's lots of hidden layers, but I didn't draw them. This is just the inputs, and then the network is like a traditional multi-color content.
then can we have a interpretation of hidden layers?
Yeah, so we looked at that and didn't see anything that's particularly useful. So I think what you're asking at is if you look at facial recognition and you can look at the lower level features and then see what highlights them, and you can see that there's an eye and one filter, which are these kind of different of the not the layers, but the parallel structures that are learned to be orthogonal in the network. I mean, you can trace them back to see what structures they're learning.
Sorry,
that did not give us anything that was interesting in this case. So there wasn't an analog of a nose or an eye or things that the different parts of the network were learning.
I mean, meaning of physical meaning of hidden layer in some hidden layer interpretation of about physical something.
Yeah, but how do you get a physical interpretation, right? You have to look at it and then map it onto something that you can put words to, and we couldn't do that. I mean, you try, and if it doesn't work, it doesn't work. I mean, I think our vocabulary for describing jets is rather limited.
Thank you. I got it.
I have a question about the general idea.
Go ahead.
So could you move to the first page, maybe? Like where you mentioned about the difference between the classical approach and the modern approach.
Oh. Yeah, what I mean here?
Yeah, yes, exactly. So here you mentioned that classically we use the machine learning to validate physics, while we're trying to use the machine learning for validating algorithm instead of the validating physics. But here I am still questioning about, so because we want to do physics, the machine learning should give some new features about the physics anyway, in order to make sense. So then the question is how validating algorithm can have a meaning, meaning in physics, like, because if you want to find out the new features in the physics, then just validating the algorithm that we invented is not enough to invent or make new observations about physics, because otherwise, I mean, anyway, it will not involve any of the new kind of physical features like or models if we just don't.
Yeah, I know what you're saying. I agree with you, and I don't have an arrow going back here to physical insight because I don't know how to do it. I mean, again, this is really just what's going on. So when the traditional approach, you really can go and see which of these variables are working and then validate your physical insight. Here, it really is, you're plugging it into a particle net cloud architecture, and it's able to tell tops from backgrounds, and you have no idea how the cloud architecture is working. So you can't learn anything about tops or anything about backgrounds. It's just very hard to probe these things and figure out what it is learned. People have tried, but as far as I can tell, the only things that you learn from these are the things that you already knew. So they'll say, did the particle net learn that tops have 3 subjects? And yes, of course it learned that. Did it learn there's a W in there? Yes, it learned that. So it's learning all the stuff that we know how to ask it if it learned. But the real thing is that it's learning something else. Because if we know all the stuff we learned, we're on this side and it doesn't work as well. So somehow the thing is that the machines are learning stuff that don't fit into our traditional categories, and we don't really have the right language for it. We can always pigeonhole it. You can mold it into the thing that we're looking for, but it's very hard to find something that you don't have the language to describe. And I think machines just have this deeper, more machine-centric language that we don't know how to translate into back into our physical insight. Our language for describing physical insights, like what would be considered a successful physical insight, is rather limited. I don't know of any examples of something we could learn that we didn't already know. And that's really the problem.
So if I've taken it correctly, then can I just can I understand that like now nowadays people are just trying to make machines that are partner which can have a better language than ours for describing the nature, or?
No, I mean, geez, I don't even know what that means, better language than ours. Right now, what they're trying to do is discrimination tasks, trying to find, classification, discrimination, regression, better discovery, reach, and colliders. They're really practical tools, right? You don't have to know what the physics is to be able to tell if you found, right? I mean, the holy grail of this is you run some machine learning on the collider and you see supersymmetry, right? And once you see it, then you can go back and analyze it however you like with physics, right? But the goal here is really to knock the backgrounds down so much that the signal will jump out. And once it does, no one will care that you use the machine learning to find it, because if we know where to look, then we can go back and then revisit it with the traditional approaches.
I see.
That's how. But again, if there's no new physics there, I don't know how you're going to succeed that way, and so you have to figure out something else to do with it.
I see.
But again, we're in the very early days of this, so I think this is a great. You're all young and interested in this field, and this is really the problem that needs to be solved in the next 5 years. We solved the discrimination one, the classification one. We didn't solve the interpretability one, and it's very, very difficult. But I think there are.
I see it. I see it. So
yeah, and I should say this
validating
is physics, right? Every area of machine learning has this interpretability problem. Everyone wants to know how to tell what their machines are learning, right? No matter what you're doing. If it doesn't have to be particle physics, right? It can be geology. It can be self-driving cars. You want to know how it's knowing, if it's learning to translate papers, or it's you want to know how it's doing it, right? You don't want it just to work. You want to know why it's working, so you can figure out when it's going to break.
Yeah, exactly.
So I think there's progress, and I think there's hope. It's just we're in the early days yet, and right now, again, we're doing this taking these tools developed for other purposes and applying them here. We need to really start developing our own tools and understanding them in the context of physics applications.
Got it. Thank you.
Any other questions?
Just one question.
Yes.
So when you train sets, your bias can creep in, and in our problems, in Topcock or whatever, how can you handle this bias problems?
What kind of bias do you mean?
Yeah, I mean when you train, then you have to make decisions that this is the gluon jet or this is a quark jet, and who does or how you make that as a training set. How do you say this label?
Yeah, so that's a great question. There's different aspects of it. I mean, there's an aspect fundamentally. There's not a well-defined idea of what a quark is, because it doesn't. It's an unstable particle, and in QCD there's interference between quarks and gluons, so you can't actually tell. There's not an infrared safe definition of quark versus gluon. Practically speaking, what we do is we run Pythia with, say, PP to glue, and run it with PP to quark, and those are our truth level samples, and we use that for training. But part of the point of my whole section on weak supervision, which was, let me see if I can go back to that. These ideas here of learning directly from data, is that you don't need to have labels at all, right? You can just train it on different areas of different experimental samples, right? Just really take literally the set of data with dijet events and take the set of data with W plus jet and look for differences. And those differences will be dominantly quark versus gluon differences, but it's a well-defined thing. And if you find some difference, then you can use that to characterize supersymmetry samples, which might look more like the W plus jet sample than the dijet sample. Or they might look less like it, but either way, if you have some way to tell them apart, you can use it to help, enhance the background or enhance the signal. So I think the weak supervision approach sidesteps a lot of those fundamental questions about quark versus gluons, but then again, you don't know how universal it is. You don't know if you're not finding quarks and gluons, you don't really have a physics interpretation. But from the simulation point of view, yeah, we have a well-defined thing. We just run Pythia with quarks. From the data, it's of course much more subtle.
Can I ask one question? Can I ask one question?
Yes, please. Of course.
Thank you. Thank you for your nice talk. Actually, you showed us the top-tagging comparisons. Could you show us again?
I didn't understand.
So previously you showed some slide for top-tagging comparisons.
The top tag
For-
comparison, yeah.
Yeah.
This from
Yeah, that one, yeah.
I can
Yeah.
pull up the paper if you want. Top tagging was this. Machine learning landscape of top tagging.
Okay.
Yeah,
So
what
my
do you want
question-
to know about it? It's a
Yes, so my question is, will not be about the detail of the paper. Actually, my question is about the performance of the various top-tagging machine learning models. In your slide, for example, the particle cloud, the particle net in the category of the particle cloud, in your slide, tops the other, the performance of the top tables. Then, to me, I think that the innovation point of the particle net lies in some new clever representation of data rather than encoding some physics, some clever physics structure into the machine learning frame. So one thing I expected to see is that the theory-inspired model like LBN or LoRa or energy flow polynomials you showed in your slide can might top the other models, because I think that theory-inspired machine learning model can be a good way for physicists like us to contribute. Yes, so I think it's a good approach for a physicist to contribute. And I'm a little bit wondered why the machine learning models like theory-inspired model could not show some slightly worse performance than other particle cloud models or image-based models. So could you add some more comment on this your some personal perspective on theory-inspired machine learning models? Maybe my question is not well delivered.
I'm not sure. There was some interfere feedback, and I didn't quite understand everything you were.
Yes, so okay, so but let me summarize my question. Could you show your slide rather than here.
This one?
Yeah, that table.
The table.
That one. Yeah, then here the best performance is from the particle lab using particle cloud.
Particle net. Yeah. This.
Yeah. Yes. Then, so one might expect that as a physicist, then the machine learning models inspired by theory might show the best performance, but the result is not.
Yeah, I mean, I should say, I'm not so convinced that this is that much better than any of these, right? I mean, these lines all sort of go on top of each other, and I think there's some statistics in the sample dependent. So, as I said, this is, there's only 146 background events out of 200,000 surviving.
Yes,
So if you look at one that's, half as good, there might be 300 background events surviving, but this is a sort of small number, so it's not clear if it's, statistically significant, but it's not that different. I mean, you really need an order of magnitude bigger sample to really distinguish these and tell what's going on. And I think the study, this community study, which I wasn't involved in, tried to make some effort to figure out whether they were all doing the same thing, and it didn't really work. I mean, they just couldn't, like you can ask, is it the same events being misclassified or not? And they sort of in the end gave up because there were 100 different authors. people couldn't do it. So I think there's room for improvement here. I think having all of these, well, the goal originally was to figure out how they're different and why they work, but that didn't succeed. So there's still more work to be done there in understanding what these methods are achieving. But I encourage you to read the review, and you know, there are various insights scattered throughout it, even though it's kind of a Frankenstein review put together with different authors. But there's still a lot of good insights.
Okay. And could you add some perspectives for Fourier models?
Have some what?
Some perspectives for Fourier models.
Perspectives for
Perspectives for the Fourier model, like LoRa or LDN.
Can you type it into the chat? I can't understand what you're saying. Sorry.
Oh, okay. Then I think my case is too long, so let me ask another time, another chance.